In this installment, we will look at work. I want to first start with this scenario of Kevin. So Kevin has a chair that has a mass of 8 kilograms. He drags it across a room with an average force of 12 newtons. So let's just put the numbers aside and see if we can understand what's going on here. We've got the chair, and we have Kevin dragging it. And so he pulls it a distance 2 meters. And it's pretty easy, without any physics formulas or any numbers, for us to realize that he did some work in dragging that chair from one location to the next. So when we then say he pulled that chair, dragged that chair 4 meters, if we were to compare the amount of work he did, it's very easy for us to see and say that he did twice as much work. So however much work he did with 2 meters, let's say that's W, if he dragged it 4 meters, it would be 2W, or twice the work. That seems pretty easy to understand as a concept. And now let's imagine he's got 2 identical chairs that he drags. Maybe they're stacked on top of each other, and he drags those 2 chairs. Now when he drags those 2 chairs 2 meters, we could see that it's also pretty easy for us to understand that when he drags that 2 meters, he will have done twice as much work as he did with dragging 1 chair. So we would then say that with 2 identical chairs 2 meters, it would be twice the work. And then when he drags those 2 chairs to a distance of 4 meters, he would have done 4 times the work, twice as much work in dragging it 2 meters. So if this is W, 2W to here, he did twice as much work as dragging those 2 chairs to 4 meters. So we could then see that it is 4 times the work going to 4 meters. So we have a situation that we can see that the work is somehow directly related to the distance that they are dragged. If whatever happens to one happens to the other, I double the distance, I double the work. We can also see that the work is related to how hard he had to pull those chairs, or what we might say is the force. And by doubling the force, going to 2 chairs, we do twice the work that we've done. So work is directly proportional to the distance. It's also directly proportional to the force. And that leads us to the formula: work is force times distance. So if we go up to the top and we look at our definition of work, it is the product of the average force and the distance over which it's applied. And energy, its definition, if we can look at the word energy, is the ability to do work. And work, of course, is the product of the average force and to the distance, is the product of the average force and the distance to which it's applied. So therefore, what we can see is there's this very tight relationship between energy and work. So in some instances, we can certainly say that the work done would be equal to the energy expended. The work done by the subject, let me just rephrase that, by the subject, is equal to the energy expended. And as we're discussing work, we should mention 2 different types of work that we'll want to come back to. And those 2 different types of work are useful work and unuseful work. And so when it comes to useful work, the energy is stored. In unuseful work, the energy is degraded. It is not available to do useful work. And this distinction may not make a lot of sense right at this moment, but it will as we look at other examples. And so let me illustrate this by talking about what happens to this work, this energy that was done in dragging the chair. So if we have that chair, we're now looking at a top view, that chair that's being dragged around like so from here to here. Well, where does that work go? Well, what happens with that work is that there is friction between the chair and the ground. And that friction between the chair and the ground warms up. It warms the chair and the ground through friction. So in fact, this case, the force that's being applied, this constant force that's being applied as it's being dragged, is actually against friction. The force works against friction. And so what that means is it generates thermal energy, Q, and that's what's illustrated by our magenta coloration there, that the ground there is heated up. So is the chair, and that's where the energy goes. Well, that energy is no longer available to do something useful, in the sense it was in the roller coaster. So the roller coaster, the motor was doing energy, raising the roller coaster up to its high point. That work went into the potential energy, that's gravity, the gravitational potential energy. So that energy, all that work that was done, all that energy isn't lost. It's stored in the position of the object. So it's now available to do useful work on that object. It can then increase its speed, and that speed then, that energy is available to, that kinetic energy is available then to do work to increase the potential energy, and so forth. So in that sense, when we're looking at the mechanical energy of the roller coaster, well, the energy is available throughout to do more useful work. But in the case of friction, that energy is lost. It is degraded energy. It is no longer available to do useful work. So we have our formula: work equals the average force times the distance. Now, if we were to calculate those numbers, it's a simple matter to plug in and say we have an average force of 12 newtons and we had a distance of 2 meters, so that's 24. And when it was times a distance of 4, that gives us 48. And when we pulled 2 chairs, the force would be twice as large. So 24 times 2 is 48, and when we pulled it 4 meters, 24 times 4 is 96. And so we can see that 24 is W, 28 is 2W, and 96 is 4W from our example calculations up above. So we have our formula: work equals average force times distance. Now let's take a look at the dimensional analysis behind this to see what the units of energy and the units of work are. So we have work is force times distance, and force is m delta v over delta t times the distance, and that then is units of kilogram meters per second times meters, which is kilogram meters per second times 1 over seconds times m, which we can see a little more clearly is kilogram meters squared per second squared. So those are the fundamental units. And when we get very wordy with these, sometimes we create a new unit, and that unit of energy, that unit of work, is a joule. So 1 joule is 1 kilogram meters squared per second squared. So I would like to come back to a question about the formula, and that is the formula really about distance or is it displacement? Well, we can answer this question. I mean, ultimately that question comes down to the difference between distance and displacement is, does direction matter? What role does it play? Well, let's say we've got our formula: work is average force times the distance versus work equals the average force times the displacement, delta x. Let's consider those two cases. So if we have I'm going to draw a top view here like this. And let's have in our, we'll do a path here. So if we take a yellow path like this, we drag something from the beginning to the end, we have a distance. Work equals force times distance. And we can see there is a force that would be applied over a distance. If we look at the displacement, we have a number. Now, depending on the coordinate system, it might be, it might be positive x or negative x or something like that. But there is a number that comes out of that. And what becomes readily apparent is if we do the same thing and say this is the path, the blue, where we started in one location, we clearly covered a distance and brought it to the end point. We went all the way around this circle like running in a track. Do we do any work? And the answer intuitively tells us that yes, we've done some work in this case. We applied a force over a distance dragging that chair. So clearly that formula distance works. Now if we look at the displacement, the delta x is 0. So in this case, if we were to say that the work we did was 0, that would not be true. And so that's one bit of evidence that the formula we have is work equals force times distance and not force times displacement. For if it were displacement, then clearly in situations where we've done work, we would say that no work was done. And so since we are using distance instead of displacement, we say that work is a scalar quantity. It does not have direction. It does not have direction. And so this is the work that has been done by a subject. And that subject is a person, a machine, or something like that, okay? And that is different from the work done on an object. All right, and we are not going to talk about the work done on an object right now. But what's key in our look at work so far, we've been talking about the work done by a subject, an actor. So in this case, we've finished our initial look at work, the work done by a subject. We see that there's a difference between useful work and unuseful work, and we can see that we can intuit the definition. We can inductively come up with a formula to calculate work based on a very common understanding that we would all have, or anyone would have, in looking at a physical situation. In our next installment, we are going to look at work being done at an angle, and we'll see exactly what that means in the next installment.